No. Take some water.
So your talk is Brazil or São Paulo?
None of them. No, it's Masjuan.
No, you just brought your talk, but we didn't put it here, right?
Right. Well, maybe we can try. No. Oh. Antonio, did you have a virus or something? Qué raro, ¿no? Vols dir que potser apreta, no? O fem al revés? És molt sensible, doncs, no?
So if you want to start, you can. I'll put your talk here. And if it's blinking, then you can also start. Okay.
No, but still.
Starting is not an option. It's done, it's here. So, take the other cable. So remove this one.
Right. Okay.
Put this one. Is it there?
It is. Great. Thank you, Theo. Well, good afternoon. Sorry for the delay. Before starting, I'd like to thank the organizers for the nice invitation to come here to discuss this topic with all of you. This actually is going to be a continuation of the discussion we had already. Part of the introduction has been already covered, thank you, previous speakers. And this is a work, which is actually an ongoing work with Jen Rerler, who is also here, and Hubert Spitzberger. And it's about determining the heavy quark masses with this relativistic sum rule, okay? I mean, I don't need to motivate, but I like to add on one extra point from why quark masses may be interesting to get it very, very precise. And you may have heard already these, say, recent years about anomalies in B and rare B decays. There, to calculate form factors, you need, from the perturbative QCD part, you need as well to get the mass of the quark as an input. And since you are seeing anomalies, getting this input precise enough is also important. The rest of the things were already mentioned. I think as well is an interesting and hot topic as well. So we have already seen the different ways to get the quark masses. Antonio spoke about this thing, and there will be talks on lattice as well. I like to focus on this, the third one. And this is a slide, an overview, just to give you a flavor how it is the community thinking about this thing. So when you go outside of this community and you explain that you are working on quark mass determination, they say, really, still you do that? No? See, they should be already very well known. No, look at this. These are different groups, not different publications, different groups working on these things. And there are many, many different, in the recent years, approaches to get these coefficients, these terms, these parameters. So they are really important. There's a lot of work. This is for the charm and this is for the bottom, which says that there's a lot of things to learn still. And so the idea that I'm going to use was already explained briefly by Andreas before, and this is the use of a sum rule relating the R ratio with the calculation of your correlator. So this is for the charm region. You have a lot of information, experimental information on the threshold, where you see here downstairs, where you only have, say, 3 active flavors, up, down, and strange. And at some point, the charm appears, and then the cross-section grows up. So knowing this thing, you expect to have the information of the value of the quark mass. And to do that, then you will see that your measurement R, the ratio, say the E plus E minus 200 over the lepton one, is going to be split in 2 different parts. This is, say, it's going to be your background, and this is the thing you are interested in, where your quark will appear. And here, in the part of your quark, there will be different contributions. So a resonance part, say, these bone states here, and then there will be some threshold, so here, and then a continuum. So you have these different pieces there that you like to take under control to get the quark mass. And then the point is, to elaborate a bit more on the meaning of the sum rule, is that you will, using the optical theorem, you relate this thing you measure with the thing you calculate in this way. And actually, what you establish is a set of relations between these things. So this is your, say, this is the thing you measure. Here are, you have the Cauchy sum rule, so Cauchy integral. Okay, and this is what you relate with the thing you calculate, this correlator, this is the heavy quark correlator you can calculate. And then when the external momentum goes to 0, you establish a set of relations between the two parts, left-hand side and right-hand side, and these are defining the sum rules. Okay, it happens that the correlator can be expanded, and this is a way, this is a showing of that. The Taylor expansion of your correlator relate to the moments I showed you previously, and they have all these coefficients. They have been a lot of work to calculate them, and they are known to alpha cube for several moments, and this is a schematic view of how they contribute. These are the different moments, and here the different alpha orders. You see that you're getting more and more precise, adding more terms. So this is the sum rule you're going to use. And then, so on the left-hand side, you have the theory, the thing I was showing you before, okay? And on the right-hand side, you would put your experimental information. That would be the standard thing, and then you will solve this equation. There are subtleties as always, because what you measure is not directly the quark contribution, but you will measure the full R. The experimental data have to be split into the light quarks and heavy quarks, and there are some recipes for doing that. The resonance part will be coming here. They would use this Dirac delta representation for them, and then you will have to define a background that is going to be the role of the light quarks getting into your charm quark. So this would define your background. That is this term, but also second order effects, but also singlet contribution are QED. Well, I went too fast here, but this is the idea. So it may happen that here you may have a secondary production of the charm coming from the light quark. It will appear here. You will put it in your background. You have the singlet contributions as well, and then QED effects that you know are calculated. You have to put them. There will be non-perturbative effects. Well, condensate contributions to the moment. You will put it as well. The formula, as Antonio was saying, their formulas are known. So you have to, the missing piece or the unknown is the actual value of the condensate. But here we were going to use a determination from tau data. So it's a different set of data that you use. And actually this is just a side note, they are important to determine the quark masses, as depending on the moment you use, you can just see that the impact is maybe of the order MeV, right? So when you have all the ingredients, then you go and proceed, no? But this is what has been done previously in the previous works, but we wanted to exploit another idea, similar to that, but putting extra ingredients. No? So in our approach, it's going to be slightly different, but we are going to avoid the local duality, which is you don't have an infinite window of experimental data. You have data from one point up to a higher point. And from that point on, the standard practice would take perturbative QCD to continue the integral. And you would do a matching there. So you say, I come from data in that way, in this side, and I continue with the perturbative thing. No? But this may introduce some a systematic error, because you are saying that data and QCD, perturbative QCD are exactly the same at that point. You can try to vary things, you can try to vary scales, but that's the issue there, no? And that's what I meant about the local duality. So instead of that, we want to propose another method using global duality. I will show you what is that, no? Then, instead of using experimental data on the threshold, we are not going to use experimental data, but only the resonance below the threshold, okay? Then the experimental data which exists is going to be used to calibrate the error of the method. So you don't use data before, you get the mass, and then you calibrate the error of that using the experimental data. And then how do you do that? No? Because you are not using data, you have to put something else. Well, the idea is then, instead of using one moment, or one sum rule, you're going to use two sum rules. And then you will request self-consistency among the different sum rules to get your result. And so the goal is to get a quark mass, right? For the charm, well, what is the idea? So you want to put, say, a second sum rule. But what sum rule you have to use? Well, you like to use different information than the sum rule you already have. For that, instead of defining your moments by derivatives, or Taylor expansion of the correlator at low momentum, standard momentum, you would define a zeroth sum rule by expanding on the other side, say at a high energy standard momentum. What happens there is that your correlator is going to diverge, as also would diverge when you take this limit, also would diverge your integral for R, but the divergence is known and can be subtracted. So if you do that, you subtract both, say, divergences. The leftover, the regular part, will define a sum rule. And this is the zeroth mass limit of the R that you would use to get the logarithms under control. Using that, you take your sum rule, and then you can do the integrals there. And this is this is the expression of this zeroth order sum rule, which is the regular part after subtracting the infinities. So this thing. Well, then you have this information. This information has nothing to do with the other moments because it's defined at the infinity instead of at 0. Okay? Then you have to supplement these parameters with data. Here, the resonance contributions from the PDG are going to take a role. And as you can see by the numbers, the jet psi is going to be dominant in this respect, as it has the largest electronic width, but also the error will also be important there. You have to take into account that at this scale, the alpha electromagnetic is going to run, and this effect, which seems small, it is not. It's not a small effect. So if you by chance forget to run alpha, you will make an error of several MeV. There's nothing you want to do that. And then you have to do this integral. So this is the massless limit of QCD, which is the expression I showed you before. And here you have a function continuum that I said I don't want to use data, but I have to do the integral. So I will use an ansatz for the form of this continuum function that I can use to integrate. What is this? This you can identify. This is the zeroth mass limit of perturbative QCD. And here you have the onset of the quark, the QQ bar, the photon QQ bar diagram. And this, if this parameter would be 1, this is the standard calculation. But we allow this an extra coefficient to modulate what is happening around the threshold region. So by introducing these ansatz, I said I want to use 2 equations, 2 moments. I will like to have 2 parameters. What parameters? Well, this is the quark mass, this is our goal, but you have an extra parameter here. So you have 2 parameters, 2 equations. You just close here, and then you get, for example, using the 0th moment and whatever nth moment, you get the result. Let me reiterate, I don't use experimental data, but on the resonance part. And then, in practice, how it works, okay? So you have to calculate all the different pieces, and then you match. The theory part would depend on the quark mass. The other part, the sum of the 3 pieces, the resonance, the continuum, they sum up to something, then you match here, and then you extract the quark mass and the lambda. And in this particular case, I use the 0th and the 2nd, so these numbers match, and the other ones are just for consistency. So you see that they agree well within error. Okay. And what is the outcome? So you have a representation of your continuum, so of the threshold region, which is different to the data point by point, because we are using not local duality, but global duality. This is the representation of this in this plot here. Now you see, this is the result of these ansatz after putting the quark mass you get and this lambda parameter you get from the sum rule, you put it there, and you see, it has nothing to do with the data, but only the integrals of that. That's the idea. So this is the representation of the global duality. Okay? Then you can repeat this exercise with different pairs of sum rules. Okay? And you have to take into account all the sources of errors you can imagine. And they are in different colors there. In blue is the total, the final result for each pair. And then these different colors talk about the splitting, individual splitting of the different sources of error, okay? In particular, for example, the resonance part means the error on the electronic width, how would they propagate. Then you have the truncation error in the fact, you may remember that the left-hand side of the sum rule, the Taylor expansion is known up to some order in alpha. Then you have an error there, no? You have to account for that and so on, no? Let me go a bit more in detail. This is the resonance contribution, and this is the truncation error I was mentioning. So this momentum is known up to a certain order in the alpha expansion. So you should attribute your ignorance as an error, and to do that we use a rather conservative estimate by giving the largest color group term from the previous order, put it there, scale it properly, and this gives you the error, no? And as you can see, across the different pairs of moments, this is a large, it contributes, it's a large error. I would rather say that these are actually quite conservative. It's even more conservative than varying, or say the impact is larger than varying the scale by a factor 2 up and down, no? And the other source of error then, it's coming from the experimental data, which you actually have, so you use it, no? What you do here is to say, okay, let me calculate the numerical moments for the energy window for which data exists, for the different collaborations, say, and you calculate these integrals, these moments, by, say, sort of trapezoidal integral, if you like. These are the numbers, I mean, just to show you, forget about that. And then what you do is, in this small region, I use the experimental moment to get my free parameter lambda. That is the area. So I have here a formula, an ansatz, that depends on two parameters. I fix the quark mass that I had before, coming from the theoretical sum rules. And the other one, the other parameter, I use this value that is coming from the 0th moment on the experimental data. And then you get immediately this parameter lambda, which is going to be different, or not, what you got before. Well, you get this number, and then you put it back to get the charge mass onto the second order, third or fourth, and then the difference induced to the quark mass is a source of error. And these are the source of error you get. No? Okay? This is to show you how it works. I showed you before, no using data was the red curve. Now that you use the experimental moment, it is the cyan band. It overlaps in the lower part and overlaps, and the width of the cyan band comes from the experimental error. Okay. Then on the condensates, as I mentioned before, we use a parameterization or a result coming from tau data, and we include it there as well. And then the last source of error is the uncertainty on the value of the alpha strong at the Z pole. Well, that it induces, well, you have a parametric expression for that, so that helps to, say, modify the result as soon as new results are coming from there. So you sum up everything. So the result, if you look at what, from different pairs of moments, that you look at the result which has the smallest error, is this one, the one that relies on the second and the 0th moment. And here this expression means that you have to put your the error of alpha strong at the Z pole here, you put it there, and then you will get the result. Okay, here is just for, say, for an amusement, if you like, how this method will work if you would do the same exercise by expanding in alpha. How you see it nicely converge here. You also see how the errors have been evolving, no? Particular, going one alpha order more, you gain specifically on the truncation error from the theoretical part. No? That's obvious. No? But also, curiously enough, the error coming from the alpha strong, you are now more sensitive to that. No? So it's a purple one. Well, just comments, no? Okay, so I was showing you results by using the 0th and the second moment, but you can wonder, how do you know what pair you have to use? No, I chose the one that has the smallest error. But having so many pairs, why don't you restrict yourself to that? No? Okay, let me just add a comment here. you are taking the gluon condensate. You may have, we already discussed, Jens was asking Antonio about that. Higher order condensates that will show up to the highest moment. So say, let me don't use these things and stick to 0, 1, 2, and 3 moments. So we have different 4 moments. And I like to extract, I don't want to marry to only a pair, just get something between them, no? A merging of all of them. So you can do a chi-square fit to that. So I'm combining things. The idea is, instead of using a pair, 3 moments, for example. For that this is just a detail. You know that the moments are correlated, especially the 1, the 2nd, and the 3rd. They are correlated. You will introduce a correlation parameter. You do that. The point is, because there are many details here, the point is that whatever you do, the results are super consistent. No? Using 1, 2, or 3 moments. So 3 moments in this way, or you correlate ones and not the other, and so on. No? Very, very nice thing. No? And this is, at the end, the result you would get, comparing to other things. Okay, I'd like to discuss now the bottom case. As you can imagine, it's going to be very similar. But there are 2 subtle points I'd like to further discuss. The first one is that it turns out that the mass effects on the perturbative QCD contribution are larger numerically in the bottom case than in the charm case. So when constructing the zero sum rule and also the ansatz for parameterizing the threshold region, we only use in the charm the part which is a massless thing. But now for the bottom, you are also like to include the mass corrections, and the reason is that for the charm, it happens numerically that this term here and the next one basically cancel to each other. So the contributions from the mass corrections are smooth there. But this accident doesn't happen here in the bottom, so you have to take them into account. So this is the plot. This is the showing of what I'm saying. You know? This is for the charm. This is this factor lambda that can be, say, massless or massive. If it's massless, this solid line. If you put the mass corrections, this is a slightly different, around 2%, quite smooth, okay, continuous here. So these are mass corrections. If you do the same, but for the bottom, you see that mass corrections are, is effect around 8% or so, it's larger effect. But which is more important is that the energy dependent on that is pretty different from respect of this one. Before we had one coefficient, lambda, that was slightly larger than 1, absorbing these effects. Now, if you want to do it correctly, you will have exactly the same parameter, but you would like to put the more terms on the mass corrections in order to be able to use the massive limit of the ratio. Okay, that's a subtle point, but you do it, and then you get your results there. So this is, again, different pairs of sum rules, and with the same splitting of error, and the color code is the same, and then you get your result. For example, using the 0th and the 6th sum rule here. I didn't show that before, but I wanted to show it here, that when you do the exercise but get the other coefficient lambda, you see that the error on lambda is fully dominated by these cyan things. And cyan refers to the experimental moment. So you do the same as we did before. You have your experimental data in the bottom case, and this induces a large effect on this parameter lambda. So when you go back, this explains why so you're very much exposed here in the low moments to the experimental data. So that's why you like to go to high moments, say, to get these coefficients, so these contributions reduced. How you get your moments? This is a second subtlety here, is that the Babar and Bell collaborations measure directly the R ratio for the B quark, because they tag the B and they can reconstruct directly the RB. You don't need to do the subtraction we did before, but then there's other things you have to do. No? You have to correct for radiative tails of the bright Wigner, the narrow width. They will have some radiative tail. You have to correct for them. This is the orange part. Then you will have ISR corrections you have to implement. This is a method which is in the literature, so you can use it. That you have here the nice bright beginner that you have to take into account how the tail is smearing out in your data and so on. So, but you have to do that things and you get your moments. Here is, for example, the paper of Juan and Vicente and collaborators, and this to show you that using the same method gets the same result. But I'm interested in the 0th moment. That's what you use. No? That no one used that. No? And when you do that, here is the homologous of the plot I showed you before, the charm. What you have here in red. So this is the RB, right, for the bottom case. This is the perturbative QCD with mass corrections. Okay. Here in blue is when you don't use any experimental data, and in cyan is when you use the experimental moments. So seems to be shifted upwards. And this, we take it as a systematic error for the charm, which is, we take it symmetric, but is, of course, as you can see, is anti-symmetric. No? Larger band here means smaller mass, but we take it as a symmetric error. And with this, I finished the presentation saying that in this method, we use a consistency across moments to get the quark mass. We did it for the charm, and now I'm discussing with you these new results. They are still preliminary. There's maybe subtleties you like to cross-check, but the number is there. And this is this number in the charm was confirmed by using several moments. You can use 3, 4 moments in a chi-square method, no? And there is a good agreement among the different moments. And what is interesting is that the error sources are understood, no? So you can now pinpoint each of them and try to get the error as precise as you like. No? And as I was saying, no, the next step is to improve this because there are some subtleties about, for example, as I show you, the experimental bottom moment seems to be high that you would expect. No? And that's all. Thank you very much.
So is there any worry that when you do this global dualities and you introduce theoretical bias? Because essentially what you assume that in the region where the resonances are prominent, you nonetheless can approximate the spectral function by a free continuum-like. So somehow that form should work, but only at larger square root of s. But you somehow say, well, globally it's okay to kind of have a smooth function that has a square root threshold behavior, whereas you clearly the resonance is very pronounced. So you essentially say I can ignore the resonance physics on average, and well, to some approximation it is good, but when you're talking about sub% level accuracy,
indeed, absolutely agree with you, and actually that's what we did. So there are 2 steps here. First, you don't use data, okay, and you get a value, and then you replace your ansatz by the experimental moment. You replace one and you put the other. And the difference is a systematic error that you are putting to the value, to your quark mass. Okay, and that's this plot. This is what I was too fast here, but that's the idea. The red one is no data. The cyan one is instead of ansatz, data. And the difference among them is an extra source of error that you account for. And actually, it's not small. I agreed. It's not small. For the lowest pairs, it is around 6 MeV. I'm quoting around 8, 9 MeV at the final error. So for the smallest one, it's important. But it turns out that when you by combining both moments, 2 moments, the 0th and nth, you are balancing well these things. The 0th moment is well exposed to these effects, while the highest ones are really very little depending on that. I actually have a plot, may be useful to discussing further these things, sorry. This one. So here you have the different moments. These effects we are discussing are the cyan ones. You see, when we use the 0th moment, we are fully exposed to these effects. But then this is for the bottom. But then you combine the 0th with one of the others, which are very little sensitive to these effects. And then that's when you see the constraint. No? One determines the quark mass, and the other one determines this pre-parameter that you use actually to balance this effect.
Okay, thank you.
Welcome.
Other questions?
So I was wondering, how do you correlate the perturbative error between different moments?
In the chi-square part of the discussion? That's what you mean? This, we put a, yeah, very good. This is an effective parameter, rho. This rho accounts for the correlation across the moments. But this is an effective parameter, and it is an outcome of the fit. So you have a fit, a chi-square fit, that has a quark mass, this lambda parameter that accounts for the ansatz, and if you put more moments, you can put extra parameters to be fitted, and rho is going to be this thing.
I think my question was more about the truncation of the perturbative series, right?
How we account for the error?
Yeah, and okay, how do you do this if you're using different moments?
Here, that we use this formula for this error here.
Yes, so you assume that the arrow goes in the same direction for each moment, or?
No,
Okay.
it's completely uncorrelated in this respect. Yeah, that's that. Yes, definitely. Yeah, you could correlate them, but we don't do that.
So I have a question regarding
Sure.
the massless perturbation expression that you use. So you're using fixed order expansion of the. Did you investigate? Because you do the integral at quite low energy. So in principle, you could also organize the perturbation series in another way, like contour improved or some other way.
Mm-hmm.
Did you
No, we
check
didn't.
if this gives
No.
some contribution? Because of course, these effects are going to be less important at higher energies. But you started.
No, we didn't explore that. But that's a good idea. Thanks. No. Mm-hmm.
Okay, since we are here, I mean, why do you take this coefficient? Or let me ask the following. I don't know. This coefficient C3n is of order 1, taking out all these factors? The one that is known, maybe to the...
No. What coefficient?
I mean,
This one?
This one is obviously will scale as you have the formula below.
But
The question is that I would also expect this coefficient to be large,
this is large. This is large.
even larger.
Even, you would expect, this is the largest term that you have here. So among the different terms, you have the...
But the number that multiply this is order 1? This is my question.
No, it's no, this. So the global factor here summing up is this large number.
Yeah, but I think the question is, you could have a number in front of this. Could be 10 or 15 or 20, right? Or
No.
he's asking for the one that we know how this
No. For
scales
example,
to see,
this explains. For example, if you use the same criterion, but for the previous, say, in the alpha expansion 1 order less, and you cross-check, this is what you're having here. No? So this is the error using this formula, but 1 order less, with respect of the known value. And you see that so this is, you are always overdoing with the error. Okay, so this is going 1 order less, order 3 or order 4, order 2. And you instead use this formula, the homologous for each order, no? And compare with the known moment. So you are doing an error by a factor 2 at least, no? Or here even larger.
Okay, the one below is the theoretical expression.
The one, exactly. And you compare on the numerator, but with this homologous formula.
Okay.
So you would expect.
For you give a determination of something which is this lambda b.
Yes.
Which actually you have in the Minkowski. No, I mean you.
This is in that. Continue.
Or maybe could you show the formula? I mean, this is the.
Let me see. Where am I?
Yeah.
For example, this one. Yes.
This one.
What?
This is a formula that you put in the Minkowski and then you put inside the integral.
Inside the integral.
And then you fit this.
Yes.
What is the interpretation that you give to that? Because to this number, because you give a number with an error.
Well, this is an auxiliary.
I mean, in the Minkowski, this would be wrong. I mean, because obviously it doesn't fit well the resonances.
No, that's true. No. You use it from threshold on in this global view, and the interpretation. Let me show you here. This is the idea. No? This lambda parameter accounts for this, say, this difference of the quark mass correction over S in the perturbative QCD expansion. Say, if you would have I would say all the mass corrections put it in the formula, lambda would be 1. But it's slightly positive, what you get. And it accounts effectively by this coefficient, or these terms in the expansion. But it's an auxiliary parameter that you use.
Is that?
An auxiliary parameter that you use to correlate the two moments.
Pere, can I ask you again, what is the blue line related to the first question in the plot that you showed of R? You showed the...
This thing?
Like a few transparencies later. You have a plot where you have the cyan and
cyan,
the red.
okay.
I didn't understand the cyan one because the red one seems to be better.
For the charm, for example. Okay,
yes.
we have
yes,
here this one. Okay.
So what is the cyan?
Yeah, great. Thanks for the question. So the red one was fully theoretical, but then you can say with all this window you have experimental data, you can calculate the experimental moment from this small window, okay? From the threshold of the pseudoscales up to the last energy point. And you can experimentally calculate the moment, okay? So from this point to there, you can use the experimental moment to get the lambda coefficient instead of using a second sum rule. So you substitute, before all the game is using two different equations, two different sum rules, sets of equations. So now in this game, you take one out and you put your experimental moment.
But I don't understand the curves. What do they are R or they're not R?
These are R.
So
Yes.
the blue curve is R.
Yes. Blue curve is R using the ansatz, where in the input you use lambda extracted from the experimental moment. And that was the question, how you get... And this induces an error, the systematic error of the, say, it's like the model systematic error, no?
But then when you put the experimental, when you say that you replace your fit by the experimental, you only do in this region from 3.8 to 4.8.
Exactly.
When you, and from 4.8 to infinity, what you do? You take your...
No, you don't need, in this particular exercise here, to get the error from the experimental data, you only work in this window. And you say, I have this window for which I have experimental moment, and I compare, but for the same window, the ansatz with a free parameter.
But from there you would only see the difference, a portion, I mean, this could affect, I mean, you are using, when you get the number of the bottom mass or the charm mass, you do the integral up to infinity using your formula.
Yes.
And from here, you only see the difference associated to this specific region, but using your formula may propagate the error because you have...
That's true, but from here onwards, the formula would be the same for both cases, and will cancel out, right? In this particular case. So we stick to the window where you have really experimental data. Of course, you would have more data, then you could do it, no? You extend the window. No?
Any other urgent question?
So no duality, Antonio, here. You don't use local duality. So just stick to this window.
So if I don't see any hands, so let's thank Pere again.
Thank you.
So we're a bit late, but I think that especially because today is the first day, I think we should really have 1 hour and a half lunch because we don't even know where to go for lunch, right? This